Let us start the discussion on photoelectric effect. What is this phenomenon? When electromagnetic radiations are incident on metal surfaces, electrons are emitted. This is called photoelectric effect. It was discovered by Heinrich Hertz in 1887. This discovery was made by Hertz during his experiments in producing electromagnetic radiations. We know that Hertz was the first person, who to produce, transmit, and detect electromagnetic radiations, radio waves in this case. That was in 1888. So during those experiments, he discovered photoelectric effect also. What is so unusual about this phenomenon, photoelectric effect? So what is after all happening? Electromagnetic radiations are incident on metals, a metal surface, and electrons are emitted. Let us consider this analogy. On a seashore, water waves are coming and they are displacing, they can displace, if they have enough energy, they can displace pebbles from a beach. Okay. So in the same way, we can have a plausible explanation of photoelectric effect like this. Light waves carry energy. We know that when light is incident on a metal surface, by light I mean electromagnetic radiation. So when electromagnetic radiation is incident on a metal surface, some of this energy may concentrate on the individual electrons in the metal and displace them. Okay, just like the water waves displacing pebbles on a seashore. Okay, the energy in the light waves, when they are incident on the metal surface, some of this energy may concentrate on the electron, a few of the electrons, and this energy will be absorbed by these electrons, and the electrons can be displaced. So this is very easy to explain, apparently easy to explain. So what can be unusual about this phenomenon? Let us see this. There are 4 experimental findings about this phenomenon that could not be explained by a simplistic model of water waves displacing pebbles. Okay. So this simplistic model, that means just like water waves displacing pebbles on a beach, electromagnetic waves can displace electrons from a metal surface. This model or this explanation doesn't work because there are minimum 4 experimental findings we can identify about photoelectric effect which contradict this simplistic model. Let us see what these experimental findings are. Consider this experimental setup to study photoelectric effect. We have an evacuated quartz tube here. There are 2 metal plates. Electromagnetic radiation is allowed to incident on one metal plate. Let us call it emitter plate. Then electrons will be emitted and it can be accelerated to the other metal plate. This is called, let us say, collector plate. When these electrons emitted from the emitter plate are called photoelectrons. When they reach the collector plate, they produce a current in the external circuit, which is called photoelectric current. This current can be measured using a sensitive ammeter. The current will be usually very small, of the order of nanoamperes, so it has to be amplified to be measured accurately. Now, usually, okay, the voltage applied on these metal plates can be varied. Okay, normally negative voltage will be applied here. Okay, so electromagnetic radiations are incident on the cathode, and positive voltage will be applied here. So electrons are accelerated to the anode. But we can vary the voltage in such a way that these polarities can be reversed also. So in this particular figure, I have shown these metal plates with polarities reversed. So even though this is the cathode emitting electrons, here now it has positive voltage, and even though this collector plate is normally anode, it has negative voltage here. So when photoelectrons are traveling towards collector plate, only those electrons which have enough kinetic energy to overcome the repulsion from the negative voltage can reach the collector plate. Okay, so this is the experimental setup. So keep in mind that the voltage between these 2 metal plates, emitter and collector, you can vary. You can apply negative voltage here, positive voltage here. You can reverse the voltage also. Okay, and these are some of the experimental physics who worked in photoelectric effect after Hertz discovery. Wilhelm Hallwachs was an assistant of Henry Hertz, a German experimentalist. Alexander Stolitov was a Russian physicist, and Philip Lenard was again a German physicist. These experimental works on photoelectric effect were done during the period 1888 to 1902. Let us consider the laws of photoelectric effect, by which I mean the experimental findings or the properties of photoelectric effect. The first law is instantaneous emission. There is no time interval between the incidence of light on the metal surface and the emission of electrons. So the emission of electrons is an instantaneous process. At the moment the electromagnetic radiation is incident, electrons are emitted, and the experimental accuracy is about 10 raised to minus 9 second, 1 nanosecond. So the emission of electrons is within 10 raised to minus 9 second. That's the experimental kind of accuracy. Now, how is instantaneous emission unusual? What is the problem raised by this particular finding? Earlier I have said that the simplistic model of waves displacing pebbles, water waves displacing pebbles on a seashore cannot work in the case of this phenomenon. We cannot argue that electromagnetic waves are coming and the energy can concentrate on the electron and it can escape. This particular finding contradicts that particular model. Why? How does it contradict our simplistic model of waves displacing electrons from the metal? So in order to understand that, let us consider this particular problem. A detectable photoelectric current is produced when 10 raised to minus 6 watt per meter square of electromagnetic energy is absorbed by sodium surface. Consider a layer of sodium of 1 atom thick and 1 meter square in area. It contains about 10 raised to 19 sodium atoms. Assume that the energy in an electromagnetic wave is spread across the wavefront. Calculate the time needed for an electron in the uppermost atomic layer of sodium surface to escape the metal. The minimum energy required by an electron in a metal surface to escape the surface is called work function. Okay, so this idea we have to keep in mind. What is work function? The minimum energy required by an electron in a metal surface to escape the surface. This is called work function. This is different from the energy required by an electron to escape from a single metal atom. That is called ionization energy. Energy required by an electron to escape a single metal atom is called ionization energy. In a metal, what happens is the valence electrons are more free. Okay, because in a metal there is an array of metal atoms. So there can be, so say an atom is not isolated, there is an array. There is the collection of atoms regularly arranged on the metal lattice. There can be interaction between neighboring atoms. The nucleus of one atom may repel the nucleus of the other atom. The electron cloud of one atom may repel the electron cloud of the other atom. So because of these interactions, the valence electrons are less tightly bound to the nucleus in each metal atom. So from a metal surface, the minimum amount of energy required by an electron to be removed, to escape the surface, this will be less, significantly less compared to ionization energy of a single metal atom. Okay, and this energy is called work function. This is for a lattice. That means this is for a surface. Okay, the minimum energy required by an electron in a metal surface to escape the surface is called work function. And for sodium, its value is 2.3 electron volt. It's given. Okay, normally on a rough idea, we can say that a work function is about half of the ionization energy. Okay, it's not a hard and fast rule, but it is roughly of that order. So it is very much less than ionization energy of single atom. Okay, so let us look at this problem and let us try to calculate the time needed for an electron in the uppermost atomic layer of sodium surface to escape the metal. Let us consider the solution of this problem. The amount of electromagnetic energy incident on 1 meter square area of sodium surface in 1 second is 10 raised to minus 6 joule per second from the given data. Okay, the energy is 10 raised to minus 6 watt per meter square. So in 1 second you have 10 raised to minus 6 joule energy incident. This energy is spread over the wavefront of the electromagnetic wave. That is the concept in electromagnetic wave. Energy is spread out over the wavefront. Hence, it is equally shared by all the 10 raised to 19 sodium atoms in the uppermost layer of the surface. Okay, you imagine electromagnetic waves coming and spreading throughout the sodium surface. So this 10 raised in 1 second 10 raised to minus 6 joule energy is coming, and this energy is spread out. Since this energy is spread out over the wavefront, this energy is equally shared over the entire surface. So it is given that on this surface layer we have 10 raised to 19 sodium atoms. So all these 10 raised to 19 sodium atoms equally obtain this much energy. That means energy gain per atom per second is in 1 second you have this much energy. There are this much 10 raised to 19 atoms. So what is the energy gained by 1 atom per second? You divide with the total number of atoms, which is 10 raised to minus 25 joule per second. Let us convert this into electron volt, because we know that in atomic levels we need only a small unit of energy, which is electron volt. So you convert this into electron volt. To convert joule into electron volt, you divide with electronic charge, which is 1.6 into 10 raised to minus 90. Let us consider only the order of the value. So that means you need to divide with 10 raised to minus 90. So 10 raised to minus 19 and 10 raised to minus 25 will cancel. We have 10 raised to minus 6 electron volt per second. Okay, so energy gain per atom per second is 10 raised to minus 6 electron volt in 1 second. Then the time required for one sodium atom to attain energy needed for its valence electron to escape. We know that in a sodium metal surface, the minimum energy required by an electron to escape the surface is 2.3 electron volt, the work function of sodium. So how much time will it take? In 1 second, an atom receives 10 raised to minus 6 electron volt. So in how many seconds this will build up to 2.3 electron volt? So you divide 2.3 electron volt divided by with energy gain per second for an atom, which is 10 raised to minus 6 electron volt per second. And what you get is electron volt will cancel. So 2.3 into 10 raised to 6 second. How much is this? You can convert this into hours. You can convert this into days. What you get is nearly 27 days. Okay, 27 days. That means, according to classical electromagnetic theory of radiation, the emission of electron is far from instantaneous. Okay, so yeah, according to our water waves displacing pebbles on the seashore model, according to that model, if electromagnetic waves are coming and spreading over the sodium surface, then it may take, if you consider this particular sample of sodium layer, and also this particular source with 10 raised to minus 6 watt per meter square power. Okay, so this particular source and with this particular sodium layer, it may take nearly 27 days for energy to be distributed, so that one electron can get this much energy, 2.3 electron volt energy to escape. Okay, so if we use this electromagnetic wave model, or if we use this model of waves coming and spreading their energy on the metal surface, and after some time one electron or more electrons can get enough energy to escape the surface, is completely wrong. When we compare our calculation, according to our calculation, it may take 27 days for one electron to escape sodium surface, this particular surface, with this particular source. But what is the experimental finding? Once the electron is once the radiation is incident, within nanosecond electrons are ejected. So almost instantaneous emission. So there is a drastic contradiction between our model, theoretical model, and the experimental finding. Let us consider the second law. number of it has two parts. Let us consider the first part. Okay, number of photoelectrons increases with intensity of the incident radiation. Number of photoelectrons increases with intensity of the incident radiation. Let us look at this result graphically. In this particular, we keep in mind the experimental setup, okay, in one of the previous slides. So frequency nu of the incident radiation is kept constant and its intensity capital I is varied. So here we have got three cases. Intensity, here the intensity is I1, here intensity is I2, here intensity is I3, and I3 is greater than I2, which is greater than I1. So what we see is that as intensity of the incident radiation increases, keeping frequency constant, the photoelectric current increases. Here on the y-axis, photoelectric current I is plotted. On the x-axis, the voltage applied between the two plates, two metal plates, between the emitter and the collector plates is the potential difference is plotted. So you can see that the potential difference can be zero. Here potential difference is positive. Okay, here potential difference is negative. So we can say that this is the potential difference applied at the anode. Okay, where at the collector plate. Okay, so here the collector plate potential is zero. Here on the right side the collector plate potential is positive. Okay, so that the electrons are accelerated, and on the left side collector plate voltage potential is negative. Okay, so electrons are decelerated. This is the potential difference between the two plates. And we have a graph like this. So this graph shows that as intensity is increased, okay, from I1 to I2 to I3, photoelectric current increases, and this is the maximum current, and this is called saturation current. Okay, so let us see how we can explain, we can look at this situation. As the positive voltage on the collector plate increases, okay, photoelectric current I increases and reaches the saturation current Is. Let us take any one graph. Let us say the intensity is I1. What happens as the positive voltage increases, the collector current, that is photoelectric current, increases and reaches a maximum. After this it is flat. That means whatever increase in the voltage, whatever be the increase in the voltage, the current doesn't increase. And in each graph you can see that initially photoelectric current increases and then reaches a plateau. That maximum current is called saturation current. Okay, now all the emitted photoelectrons reach the collector plate. Okay, why can there be such a saturation? Let us say in 1 second, I mean when electromagnetic radiation is incident, some 100 in 1 second some 100 electrons are emitted. So when the accelerated voltage is or voltage applied at the collector is zero, a few of them, let us say some 60 electrons reach the collector plate. Even with zero voltage, they have enough kinetic energy, so it produces some collector current, some photoelectric current. If we increase the voltage, accelerating positive voltage at the collector, more and more electrons will be accelerated towards the collector plate. So initially it was 60, then 70, 80, 90, and finally all in 1 second 100 electrons are emitted, let us say. So all these 100 electrons will reach the collector plate. Okay, so all, that is why there is a maximum. 100 electrons are emitted, and at this particular voltage 100 electrons reach the collector plate. Then after that, whatever be the increase in the positive voltage, the number of electrons reaching the collector plate is not increasing. It remains constant at 100 per second. That is why there is a saturation current. And what we see is that as intensity increases, the saturation current increases. So saturation current increases means more photoelectrons are reaching the collector plate per second. So that is why we say that number of photoelectrons increases with intensity of the incident radiation. This is the part A of second law, we can say. The second part of second law is the kinetic energy of photoelectrons does not change with intensity. Kinetic energy of photoelectrons does not change with intensity. How do we get this result? Again, let us look at the previous graph. This time, let us look at this part. Okay, As the negative voltage is applied on the collector plate, okay, the slower electrons are repelled before they reach the plate. Okay, let us say 100 electrons are emitted per second. They may have different kinetic energy. So initially we apply 0 voltage and around 60 electrons reach the collector plate. That according to our imaginary example. Now if we apply negative voltage at the collector plate, more electrons will be repelled before reaching the collector plate, so that photoelectric current decreases. Okay, from here to here, photoelectric current decreases. As we increase the negative voltage, more and more electrons will be repelled, so the photoelectric current will decrease. And finally, when the voltage at the collector plate is minus V0, that means negative voltage V0, then all the electrons, even the fastest electrons emitted from the um, this one fastest electron emitted from the emitter are repelled by the voltage, and even the fastest ones cannot reach the collector plate, so that photoelectric current drops to 0. This is called stopping potential or stopping voltage, because at this voltage all the photoelectrons are completely stopped from reaching the collector plate. Okay, so this stopping here, what we see is that even when you increase the intensity of the incident radiation from I1 to I2 to I3, the saturation current increases, of course, that we have already seen, but the stopping potential remains the same. Okay, the stopping voltage does not change with intensity. What is the importance of stopping voltage? The stopping voltage corresponds to the maximum kinetic energy of photoelectrons, right? Because even at 0 voltage, around 60 electrons are reaching the collector plate. That means they have high kinetic energy. When you increase the negative voltage, some of the electrons are repelled. Who are the electrons which are repelled? Those with lower kinetic energy. Okay, those with lower kinetic energy or slower electrons are repelled. So the faster electrons are able to still reach the collector plate. But when you increase the negative voltage at the collector plate, even the faster electrons are getting repelled. And finally, at a particular voltage V0, the fastest electrons are getting repelled. So this voltage V0 is a measure of the maximum kinetic energy of photoelectrons. The relationship is kinetic energy maximum equal to EV0. Okay, we know that when a charged particle is here, what is happening is deceleration, not acceleration. Okay, electrons are emitted from the emitter plate, and you have a collector plate here, and you have applied a negative voltage here. Okay, so let us say these electrons are emitted with a kinetic energy, maximum kinetic energy, Ke max. Okay, let us say it is 4 electron volt. Okay, when you apply minus 2 volt here, they are still able to reach this 4 electron volt. Electrons can still reach the collector plate. Okay, and form a photoelectric current. You increase this negative voltage minus 2, minus 3, etc. And when it reaches minus 4, what happens? Even those electrons which are emitted with a maximum kinetic energy of 4 electron volt, by the time they reach the collector plate, their kinetic energy reduces to 0. Okay, so the change in kinetic energy of a charged particle when it is moved through a potential difference V volts is Q into V. That change in kinetic energy can be increase in kinetic energy or decrease in kinetic energy. So when an electron of charge E is moved through a potential difference V0, its change in kinetic energy is EV0. So if it is decelerated and completely stopped before reaching the collector plate, then this EV0 is its decrease in kinetic energy. So initially it has a maximum kinetic energy. By the time it reaches the collector plate, kinetic energy drops to 0. Okay, so we can say decrease in kinetic energy is equal to EV0. And what is the decrease in kinetic energy? Ke max minus 0. That is, maximum kinetic energy of photoelectrons is equal to EV0. So what is the importance of stopping potential? Is it's a measure of maximum kinetic energy of photoelectrons. E times this charge times electronic charge times this stopping voltage gives you the maximum kinetic energy of photoelectrons. So the fact that the stopping voltage does not change with intensity. Okay, it remains the same even though we increase the intensity. So the fact that the stopping voltage does not change with intensity means that kinetic energy of photoelectrons does not change with intensity. That is the second law, the second part of the second law. The kinetic energy of photoelectrons does not change with intensity. Let us consider the second law in complete form. There are two parts here. Number of photoelectrons increases with intensity of the incident radiation. The kinetic energy of photoelectrons does not change with intensity. Now, how is this finding unusual? In the sense that how is this second law contradicts the classical concept about electromagnetic waves in this way. According to the classical electromagnetic theory of radiations, as the intensity of the radiation increases, its energy increases. Okay, increase in intensity means increase in energy, and hence the emitted electrons should have more kinetic energy. Okay, so if the incident radiation, its intensity increases, for example, brightness increases. If we are using visible light, we are using more brighter light. That means more intense light. Okay, so if the intensity increases according to classical electromagnetic theory, energy increases. So if energy increases, the emitted photoelectrons should receive more energy. That means their kinetic energy should increase according to classical electromagnetic theory. But what is the experimental finding? That the kinetic energy of photoelectrons does not change with intensity. This is a paradox for the classical theory. So according to the expectation based on classical electromagnetic theory, as the intensity of the incident radiation increases, kinetic energy of photoelectrons should have increased. But experimentally what we find is that there is no increase in the kinetic energy of photoelectrons with intensity. This cannot be explained. This could not be explained by classical electromagnetic theory. So this was a paradox. And also the result that the classical theory has no explanation for the increase in the number of photoelectrons with intensity of the radiation. Look at the first part. As the intensity increases, photoelectric current, the saturation current increases. That means the number of photoelectrons increases. And there is no explanation. The classical theory has no connection between number of photoelectrons and the intensity of the radiation. So in this way, these two observations, experimental observations, are could not be, they cannot be explained based on classical electromagnetic theory of radiations. Consider the third law. Maximum kinetic energy of photoelectrons increases with frequency of the incident radiation. In the previous slide, we have seen that maximum kinetic energy of photoelectrons does not change with intensity. Here we see that it increases with frequency of the incident radiation. Let us look at it graphically. Here, intensity of the incident radiation is kept constant and its frequency is increased. Okay, so we have got three different curves here. One with frequency, the inner one is having frequency, the radiation. Inner one corresponds to the case when the incident radiation has frequency nu1. The next one corresponds to the case where the incident radiation has frequency nu2, then nu3, and nu3 is greater than nu2, which is greater than nu1. Okay, and on the y-axis we have photoelectric current, x-axis collector plate potential. Okay, so towards right we have accelerating potential, and towards left we have negative potential, that means retarding potential. Okay, so let us see here how we can explain this. As the frequency of the incident radiation is increased from nu1 to nu2 to nu3, what we see is that the stopping voltage has to be increased. Okay, higher and higher negative voltage is to be applied at the collector plate to stop the photoelectrons completely. That means to make the photoelectric current zero, we have to apply V01 when the frequency is nu1. When the frequency is increased, we have to apply a higher stopping voltage. When the frequency is again increased, we have to apply a still higher stopping potential. Now, since stopping potential, so what we see is that stopping potential increases with frequency. But we know stopping potential is a measure of the maximum kinetic energy of photoelectrons, right? This shows that maximum kinetic energy of photoelectrons, or kinetic energy max, increases with frequency of the radiation. Okay, stopping voltage increases with frequency means maximum kinetic energy of photoelectrons increases with frequency. That is this result. And this was discovered by Philipp Lenard in 1902. This is Lenard, German physicist, and the 1905 Physics Nobel Prize was awarded to Philipp Lenard for his work on cathode rays and photoelectric effect. Right. So this is the third law. The fourth law is, below a minimum frequency nu0 of the incident radiation, no photoelectrons are emitted. This threshold frequency is a characteristic property of the metal. Let us again see this graphically. The data for this graph, here in this graph, frequency of incident radiation is plotted along the x-axis and stopping potential is plotted along the y-axis. The data for this graph can be obtained from the previous graph. Okay, in the previous graph we have seen that as the frequency of the incident radiation is increased nu1 from nu1 to nu2 to nu3, stopping potential increases. So we take the frequency values of different incident radiations, take the corresponding stopping potentials and plot this graph. Plot stopping potential along the y-axis and frequency along the x-axis, and we get straight line graph. If we consider a single metal, let us say potassium, we get a straight line graph. This shows that stopping potential is directly proportional to frequency of the incident radiation. The relationship is linear. For another metal, you get another straight line graph with the same slope. Okay. Now, if we consider one such straight line graph, so it shows that stopping potential is directly proportional to frequency. If we extrapolate this graph backward, okay, then at some particular frequency, this graph touches the x-axis. It touches the x-axis means now the stopping potential reduces to 0. So at the particular frequency nu0, stopping potential is 0. Remember that stopping potential is a measure of maximum kinetic energy of photoelectrons. So that means at this particular frequency, maximum kinetic energy of photoelectrons is 0. It means that no photoelectric emission. These photoelectrons cannot come out of the metal surface. So below this frequency also there is no photoelectric emission. And this frequency is called threshold frequency. Okay. So this means that there is a minimum frequency for each metal. Okay, there is a minimum frequency below which there is no photoelectric emission, and this is a characteristic property of the metal. For calcium, you have another threshold frequency. It is higher than that of potassium. Okay, why it is higher than that of potassium is another question that we will address later. But now, for the time being, what we can keep in mind is that for each metal there is a unique threshold frequency below which there is no photoelectric emission, right? How is this finding unusual? Let us we have to consider this finding along with the previous third law also, because both law 3 and law 4 are related to what happens when frequency is varied. Keeping intensity constant, you vary the frequency of the incident radiation. What is unusual about this finding is that, for example, you consider the previous slide, the third law. What happens when frequency increases, the stopping potential increases. Here also we can see that frequency increases, stopping potential increases, which means that when frequency increases, maximum kinetic energy of photoelectrons increases, right? So if maximum kinetic energy of photoelectrons increases, then it means that somehow the energy imparted to the photoelectron should increase. That means when frequency of the incident radiation increases, somehow the energy given to the photoelectrons should be increasing. But in classical electromagnetic theory of radiations, there is no relation between frequency of the radiation and its energy. Okay, hence the increase in maximum kinetic energy of photoelectrons with frequency of the radiation is a paradox to the classical theory. That is why it is unusual. Classical theory, in classical electromagnetic theory, there is no connection between frequency of the incident radiation and its energy. So here what we find is that when frequency increases, somehow the energy of the radiation should be increasing because the kinetic energy of the emitted photoelectrons is increasing. Okay, but what is this connection between frequency of the radiation and its energy? There is no such connection in classical electromagnetic theory. So this result is a paradox. It cannot be explained using classical electromagnetic theory, and also the existence of threshold frequency cannot be explained using classical electromagnetic theory. Why there is no emission below a particular frequency? There is no explanation. Okay, so now we have discussed the 4 experimental findings, and as we have observed in the one of the earlier slides, all these 4 experimental findings on photoelectric effect, which we call laws of photoelectric effect, all of them contradict with classical electromagnetic theory. Okay, what are these? Let us consolidate. What are these experimental findings? What are the laws of photoelectric effect? First one, it's an instantaneous emission. We have seen in one calculation numerical problem that according to classical electromagnetic theory, it may take many days for the emission to take place, but experimentally we find is that the emission is instantaneous. Second one, when we increase the intensity of the radiation, the number of photoelectrons increases, saturation current increases, which means number of photoelectrons increases. And also when we increase the intensity of the radiation, the maximum kinetic energy of photoelectrons does not increase. Again, this cannot be explained by classical theory. According to classical theory, what we expect is that as we increase the intensity, more energy should be given to the metal surface. That means the maximum kinetic energy of photoelectrons should be increasing, but we don't see such an increase here. Also, why there is an increase in the number of photoelectrons with intensity, this cannot be explained by classical electromagnetic theory. Now thirdly, when frequency of the incident radiation is increased, stopping potential increases, which means maximum kinetic energy of photoelectrons increases. Again, this cannot be explained. There in classical electromagnetic theory, there is no connection between frequency and energy of the radiation. And lastly, there is a minimum frequency called threshold frequency, below which there is no photoelectric emission. Again, there is no explanation from classical electromagnetic theory. So this concludes our part 1 of the discussion on photoelectric effect. Now in the next part, we will look at how we can explain these 4 experimental findings. And we know that there is no explanation based on classical electromagnetic theory. Then how we can give a new theory which can explain these experimental findings. Let us see.